In this video, we'll be going over different types of equilibrium problems and how to calculate equilibrium, how to calculate K, how to calculate change. We'll be using an ICE table for doing these problems. So here's some beginning tips for using an ICE table. So one, set up the ICE table, and we want to set this under our reactants and products. So one thing to always remember is our K value is only calculated from equilibrium concentrations. You'll see that when you read the problem, they'll give you initial amounts. They might give you the amount that changes. And in some problems, they'll give you the equilibrium amounts. Just remember when you set up the equilibrium expression, it's going to be the amounts on the equilibrium line. So the ICE table represents initial, change, and equilibrium. So when you're finding the C in an ICE table, don't forget to account for the coefficients. You'll see all these. I'll mention all of these when we start doing the problems. So you may want to refer back to this slide. If you have given amounts of all species initially, you'll have to calculate something called Q, which is called the reaction quotient, to tell which side to add or subtract on the C line, and then see the last example that I do. I'm going to do 3 examples where we use an ICE table. Generally, when you're doing an ICE table, let me show you. It's really important to set up the problem like this. So if you have, here's our reaction. A plus B makes C plus D. Your initial amounts go right here, right underneath. And then you could set up like these boxes where you have to basically fill in these boxes. Then you have a change amount, and then you have an amount on the E line. So that's what I mean by when I say line. So I'm talking about when I talk about the E line, I'm talking about this whole line right here, and the C line means these amounts right here. You're going to think of these problems as like these empty boxes. So we could actually call this, maybe we could even call this a new thing. It's a rice table instead of an ICE table. So the R, and it's important to notice like these are like segments, and you want to put numbers in that correspond to the reactant A. So A will have all these numbers, B will have all these numbers, C will have all these numbers, like an initial amount, an amount that changes, and then an amount that's exists at equilibrium. So you could think of these equilibrium problems as like these empty boxes, like here, here, here. And when you read the problem, it's kind of like a puzzle. These equilibrium problems, it's sort of like a puzzle. They may give you this information and maybe like this information, and the object of this game is you have to try to fill in like all the other information that they don't give you based on the information that they give you. So you're kind of like a detective where you have to take a little bit of information and then you have to like figure out the boxes that they're not telling you. Okay. What part C is saying right here, so what part C is saying is the K is related to just these amounts here, 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 and here. So that's what K is equal to. So K is equal to C at equilibrium, D at equilibrium over the concentration of A at equilibrium times the concentration of B at equilibrium. What part 4 is saying is something called Q. It's called the reaction quotient. You'll be reading about it in, I believe it's 15.6. This allows you to tell which way the reaction will shift if you compare Q versus K. And you do this initially. So you do this, I'll put IN for initially. So you do it with the initial amounts. It's just like K, but you do it with the initial amounts. And it's going to tell you which way the reaction will go. It's gonna, so when you compare Q and K, it's gonna tell you whether it goes this way or if the reaction is shifting this way. It also has to do with Le Chatelier's principle, which is, I believe, the last section. So you do it with the initial amounts. Okay, so let's start doing some of these equilibrium problems. So type 1 is you're going to calculate K when all the equilibrium concentrations are known. So here's an example. And then we'll set up our ICE table. So here's our reaction, initial, change, equilibrium amounts. Okay, so an equilibrium mixture of gases was analyzed, and it was found to contain this, this, and this. So, so like I was saying in the previous slide, is think of these as all these blank boxes, and we have to like fill in the information they give us and what they don't give us. So this is actually the easiest kind of equilibrium problem because they just go ahead and give you all the equilibrium amounts. So at equilibrium, H2 was found to be this, 7.38. And we're calculating Kp, so we're going to work with pressures, not concentrations. 2.46 is nitrogen. 0.166 is the NH3. ATM is H3. So we actually don't need any of this information. We don't need it because they're asking us calculate Kp. So write out your expression. Don't be lazy. Write out the expression PNH3 because I see this simple mistake all the time, like on tests and quizzes, is students they go right into solving Kp. They go right to their calculator. Don't be lazy. Write this out. Because students always forget to square stuff or cube stuff or whatever. So you'll see the bottom is partial pressure of nitrogen times the partial pressure of H2 cubed. Okay, and now that we have our amounts, we just plug everything in. So we have 0.166 squared over 2.46 ATM times 7.3 ATM cubed. Okay, we plug this in our calculator, and we get 2.79. Should be 3 sig figs. 2.79 times 10 to the negative fifth. Okay, simple. Easy. Okay, they get a little bit more challenging. That's the easiest one because they gave you the last box, and then they said calculate Kp. All right, so let's try different kinds and slightly different. So it says calculating K from the initial and equilibrium. So they're going to give you a mix match of the boxes of information. They're going to do a little bit of a mix match here. So, okay, I'm out of space on this slide. So I'm going to do this problem in the next slide and set up a nice big ICE table. So here's our reaction. It was H2 plus I2 makes 2HI. And so there's my reaction, initial, change, equilibrium. So again, think of all these things as boxes. I forgot to mention a really important thing here. It's actually, I take it for granted because it's really basic, but to get the equilibrium line, it's the amount you had initially plus or minus the change. So the equilibrium, the amount at equilibrium is the amount you had initially plus the change. So that's actually going to play a big role in how we do this problem. So again, keeping with our theme, so there's one thing in common with all these problems. So they're all different, which can make this topic hard. But the one thing they all have in common is to think of it as like this puzzle. Okay, and then we have to read the problem and figure out what they're telling us and what they're not telling us. So in this problem, if we go back and read, the amount initially, they give us this for H2, and then they give us Then they give us this for I2. And we're going to assume the amount of HI, we're going to assume that this is 0 initially. They don't really come out and say it, but we're going to assume that you just started with the reactants and you let things happen and then this will form. So we'll assume that this was 0 initially. And they tell us the amount at equilibrium. They tell us this is this at equilibrium. So let's fill in the boxes that they're telling us and not telling us. And then let's try to get Kc. So they gave us this. This was given this was given to be 1.000 times 10 to the negative third. This was given to be 2.000 times 10 to the negative third. This amount we were going to assume it was 0. Assume it's 0 initially. Then they didn't give us any of these. They didn't give us the change line here. And they didn't give us these either, these equilibrium amounts. But they did give us this. This was given. This was 1.87 times 10 to the negative third. So we need to know what this is and this is because they're asking us calculate Kc. So Kc is the concentration of HI squared, which we have. I'm going to write EQ over the concentration of H2 times the concentration of I2 at equilibrium. So they gave us the initial amounts, not these amounts. So we need the equilibrium amounts. So to get that, we need to know what the change is. So the change is going to be, this is 0 over here. So we need to know whether do we subtract or add on this side, and do we subtract or add on this side. So to answer that question, this needs to become something. We need something over here. Something has to go over. It doesn't even matter if K is super small. This cannot be 0 at equilibrium. So we see that it increased. So therefore, we can reason that this needs to go up by, there's a 2 here. So don't forget about that. This goes up by 2x. And we know that these go down because it has to go down. For this side to increase, this side must go down. So this is 1 and this is 1. So this goes down by 1x and this goes down by 1x. So to figure out what this is, we have 2 unknowns, but we could figure out what x is by using this information. So we'll use that here. So we'll say 1.87 times 10 to the negative third equals the I line plus the C line. So we'll plug in 0 initially and 2x here for the change. So solving for x, we get 9.35 times 10 to the negative fourth. Okay, so now we know what x is, so we put that right here, and we could figure out what these numbers are here and here. So we'll hold on to this for a second, so because we got to figure out what I2 and H2 are at equilibrium. So we're going to take, for H2 at equilibrium, I'm going to use this right here. So it's going to be 1.000 times 10 to the negative third minus x, which is 9.35 times 10 to the negative fourth. So the H2 at equilibrium I get is 6.5 times 10 to the negative fifth, and then I2 at equilibrium is going to be 2 minus x, 9.35 times 10 to the negative fourth. Okay, and then this number is 1.065 times 10 to the negative third. So this number goes here, and this number goes here. We know the amounts at equilibrium. So if we plug all these values in for Kc, now that we know what this is, this, and this, we plug those in to here, okay? And I got 51. And according to, if we trace all this back, the sig figs, somehow I ended up with just 2 sig figs. Where would that be? Oh, I think after you subtract from here and here, we wound up with 2 sig figs. So if you trace it back, we get 51. Okay, next problem. So this one is, you had like a mix and match of initial amounts and equilibrium amounts. The previous problem, if we compare it, they gave us all the equilibrium amounts right off the bat. Okay, here we had to, on the next one, we had to do some work, some detective work to figure out what these were. Okay, so let's try a different one, a little bit different type of problem, equilibrium problem. This one. Okay, here's where they give us all the initial amounts. So there's something there initially for everything, including the product. So we have to do a little bit of work to figure out which way this is going to shift. We actually have to calculate Q, so because they give us all the initial amounts. So we go Q is, I use the same reaction as the previous problem. So the purpose of doing Q is to figure out which way it goes. Does it go this way or does it go this way? So our equilibrium constant is 50, and we have to figure out what, this will not be 50 with these initial amounts. It's something other than 50, and our reaction must get to 50. It has to get to this magic number here. So we have to figure out what we're starting with initially to figure out which way it will shift, either left or right, to try to establish equilibrium. So we're going to go use the initial amounts to figure out what we're beginning at, what our ratio is. So if we plug in the amounts, so this is concentrated, looks like they're giving us moles. The size of the container is 1 liter. Okay, so we could just divide all of these and get moles. So we're going to get, for Q, we're going to get 2. I'm going to ignore sig figs because I just want to know which way this shifts, actually. So I get 2 squared over 1. So it's 1 divided by 1, 1 times 2. So I get 4 over 2. So my Q value is just 2. Okay, so what does that mean if I analyze Q? So K is 50. I don't have K right now. What I have is 2. So what that means is the numerator, products over reactants, this needs to increase. So the products must go up and the reactants need to go down over time. So 2 needs to become 50. That's the only way that will happen, is if products go up and reactants must go down. You can't have this stay the same, because the reason this is going up is because these are reacting, they're being consumed. So those must go down. What we just figured out is, we figured out that in this reaction, what we just figured out is on the C line, we need to subtract on this side and we need to add on this side over time. So that's what we just determined. Those look like zeros. Those are supposed to be zeros. Those are supposed to be some value. We don't know. We're going to figure it out. Okay. So, but what Q just told us was this reaction, it shifts to the right, because I don't like memorizing what to do. Oh, when Q is less than K, actually, I don't even know. I just analyze it. I just think it through every time by using this analysis. But it turns out that since Q, they have a table in the book. I don't memorize that table. I just try to like think it through, that for Q to reach K, it must go to the right. All right, so let's start this problem. Let's do this problem. So H2 plus I2, and we have 2HI here. So there's my reaction, my initial amounts, my equilibrium amounts. My initial amounts are 1.00, 2.00, and 2.00. Okay, this, so again, keeping with the theme here, that these are boxes, and we got to figure out what these boxes are. Okay, so we just figured out that Q was 2, which is way less than K. So that means that it must go that way when that happens. So this is plus 2x. Before, if you compare this to the previous problem, initially that was 0. So you knew automatically it had to go to the right. This one, we're not so sure. So you have to figure out what Q is first. So these go down over time, and this goes up over time. So that's how you knew to subtract and add on the C line. All right, so this is going to be 1.000 minus x. This will be 2.000 minus x. This will be 2.000 plus 2x. We write out our equilibrium expression. HI squared. Don't be lazy. You have to put that square right there. This whole thing will be, off if it's not squared. And you could spend like 30 minutes on this and wondering why it's not matching the back of the book. It's because you might be lazy. So don't forget to square your stuff over there. All right, so this will be, so plugging in this, the whole term gets squared. Okay, and then this goes in for this number here. So 1.00 minus x, 2.00 minus x. Okay, and they gave us the equilibrium value. It's 50.5. Okay, what we're going to wind up with is a quadratic equation that we have to solve. There's a couple ways you could do this. So we could graph this. So we could go into our graphing calculator and graph this function here. And there's actually even a couple ways you could even graph this. You could set this whole thing equal to 0 by subtracting 50 on both sides and set it equal to 0 and graph that function. Or you could graph two functions. You could graph this one and see where they intersect. What I've seen students is they actually like to graph the two functions and then calculate where they intersect. I'll tell you the problem with this method is sometimes it's actually what's going to happen on this one is your x and y scales are going to be way different. So it's going to be real hard to fit this. If you don't know what you're doing, it's going to be kind of challenging to fit this in the window on your graphing calculator. So I'll show you what I mean. So take out your graphing calculator. So here's mine. The first thing you want to do is make sure, so if you go to stat and edit, is it looks like I have some stuff in here from a previous problem. You don't need to clear that out, but you do need to go into stat plot, which was second function in this button, and we need to turn this off. So I'm going to select it and turn it off so it doesn't start graphing what I had here. Okay, so I went ahead and I went into stat plot and I turned it off so it doesn't graph, like different things. So I'm going to graph this here and take that, enter it, and I'm going to enter this in a separate line for, I go to y equals, and I'll make use of this this fraction form. So I'll go parentheses 2, and your calculator's not going to care about, excuse me, the graphing calculator's not going to care about all those decimals. So I'll put 2x plus 2x squared. Now we go 1 minus x. And then I go 2 minus x, like that. And then I'm going to put on a separate line. So notice I scrolled down to go to a separate function. I'm going to graph this one right here, 50. There's a different way to do this, but I've noticed students, they kind of like doing it this way, I've noticed. So now I'm going to hit graph, and we'll see that it's going to graph one line here. And my next line is not showing up, and I'll show you why. It's not showing up because my scale is off, so I'm not even seeing hash marks right here. My scale is way too big. So I'm going to go into the window, and I'm going to adjust this. So I'm going to go zoom and zoom stat. And actually, sorry, let me go zoom. I have to wait for it to graph now. I'm gonna have to manually adjust this. So, because I know so I'm gonna go to window, and I know my values. I'm not gonna care about the fourth quadrant. So the information I need will all appear in the first quadrant. So I'm gonna go to X max, and I know just kind of by looking at the equation that it's gonna be a little less than 10. One of the values, actually quite a bit less than 10. My scale, I'm going to change my scale to 0.2 because I'm pretty sure one of my x values is going to be really small in order for it to equal 50. My minimum is actually I don't care about the stuff that goes into the bottom two quadrants. So I'm going to set that to 0, and my y max is I'm going to have a straight flat line at 50. So I need something over 50. I'm going to put 100 for that. And for the scale, it doesn't really matter. I'm going to make it go up by, like, you could do like 5 or 10 increments. Okay, and now I'm going to hit graph. Okay. And there's the function I put on the first line, and now it's graphing y equals 50 there. Okay, so what I want to know, what I'm interested in is this value and this value. And I'm going to reject one of those values because the second one is actually going to be greater than what I started with, so that one won't make physical sense. So I'm going to go here, and I'm going to go to here for calc. So I'm going to go second function, calc, and I want to select this, intersect. So I'm going to hit 5. And I actually don't care about this line, because if I go up here, we could see that y is going to be, so when y is 50.5, x is around 2.6, which is actually greater than my initial value. So I'm going to ignore that possibility. I'm going to go to my other curve, keep scrolling, so it makes like a big asymptote way up there. So I'm going to go over here. I'm going to hit enter. And then it says where y equals 50, second curve. And I say, yeah, I want to know when y equals 50, what x is. So just choose the two curves, basically, anywhere on there. Okay, and then I'm going to hit enter. And it says, do you want me to guess? And I say, yeah. Okay, so there's x, 0.79. So close that. So x equals 0.79. The other way to do this is, so it says what are the equilibrium values. So you could plug this back in for x and then solve for hi at equilibrium. Okay, and now that we know what x is, I know that hi is this is going to be 3.58 molar. I2 will be 1.21 molar, and H2 is going to be equal to 0.21 molar. Okay, let me show you real quick the other way on your graphing calculator to do this. So I have my graphing calculator. You could just go to apps. Is actually what you want to do first is put this in. So you actually need to simplify this, actually put it in the quadratic formula. So we need it in the So if you combine all your like terms and you put it into this form, this is what you would get. So I did all the algebra beforehand, before I made this video, and this is what I have. X squared equals 0. So if you don't know how to adjust the scale, you should know this method as well. So that's what I came up with. So I'm going to pull out my graphing calculator, and there's an app that you can download. So it's in my apps here, and it's this right here. It's called Polysmelt, and you have to get the it's not Polysmelt, Polynomial Simulator, I think is what it stands for. So I enter that, and I'm going to run this program. Press any key. Okay, polynomial root finder, that's what I want. So I hit enter. And what order is my polynomial? It's the second order from here. Okay, so I'm going to select that. So it's already on 2. So I'm going to hit next. Now it's asking me what I want to put for A2, A1, and A0. So A2 is 46.5. A1 is negative 160. And A0 is 97. So now I hit solve right here. Solve. And then I get the same answer, 0.79. And this is with the bigger answer. And I want to reject that because it's greater than my initial amount. So it doesn't make chemical sense. So I'm going to put 0.79. So this way, I recommend this way if you don't want to mess with adjusting the window. So if you don't know how to adjust the window, your graph will be totally off the window. You won't be able to find the intersect from the graphical method. Most of the time, graphing actually works, but sometimes I chose actually these screwy numbers. I chose them on purpose to show you that sometimes that window can be a bit of a pain to get it to adjust right if you don't know what you're doing. So that's why I wanted to show this second method. It took a long time, but I think it's worth it because that could happen. So now for the your turns. So you're going to have to really review these slides and these problems. So here's the your turns. So here's this one. I just put review your notes. It might be like the first one. It might be like the second one. And it might be like the third one. So there's that one. And I'm going to go ahead and move to the next one. So if you want, you could pause it to write this down. So here's the next your turn. Is this one. Okay, so this one might be like the first example I did, might be like the second, might be like the third. So try to figure out which one it's kind of like and use that as a model. And I'll see what you guys come up with. It's the end of our tutorial.